Here's an orange, a perfectly ordinary orange sitting on the table, and here is a theorem, proved in 1924 by Stefan Banach and Alfred Tarski, that claims the following. Take this orange, cut it into 5 pieces, then, without stretching or squishing or bending any of them, just rotating and sliding them around in space the way you'd move a coffee mug, reassemble them, and you'll have 2 oranges, each one the same size as the original, not 2 half-sized oranges, 2 full oranges, identical in every geometric respect to the one you started with. If this is the first time you're hearing this, your reaction should be to close the browser, because it obviously can't be true. An orange has some volume, let's call it V, and volumes don't multiply when you move things around. If you take a cookie and break it in half, the 2 halves together still have exactly the volume of 1 cookie, because that's what volume means. Conservation of volume under rigid motion isn't a theorem, it feels like a definition. And yet the mathematics is airtight, the theorem is true. The pieces exist. The only way out, the only pressure valve for this paradox, is that some of those 5 pieces are not the kind of thing you could ever actually cut out of an orange. They're so pathologically jagged, so infinitely detailed at every scale, that the concept of volume simply doesn't apply to them. They have no volume. Not zero, undefined. Getting to that answer takes a few pieces. The path starts with a hotel. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, and so on. Every room is full. A traveler walks in and asks for a room. The manager thinks for a second, and then does something clever. She asks the guest in room 1 to move to room 2. The guest in room 2 moves to room 3. Room 3 moves to room 4. Everyone shifts up by 1. Room 1 is now empty, and the traveler checks in. No one was kicked out. The hotel is still full. 1 plus infinity somehow is infinity. Then a bus pulls up with infinitely many new travelers. The manager doesn't panic. She asks every guest to move from room N to room 2N. Now all the odd-numbered rooms are empty, and there are infinitely many of those, so every new traveler gets a room. Infinity plus infinity is again infinity. This is the mechanism that drives everything that follows. When a set is infinite in the right way, you can split it into 2 pieces that are each, by themselves, the same size as the original. The orange, thought of as a collection of points, has this flavor. There are uncountably many points in there, and uncountable infinities are even more flexible than countable ones. But Hilbert's hotel doesn't immediately give you Banach-Tarski. Rearranging room numbers isn't a rigid motion of space. You can't renumber the atoms in an orange and have that count as physically moving them. We need a way to duplicate that respects geometry, not just counting. The second ingredient is more abstract and considerably stranger. Consider the set of all finite words you can write using 4 symbols: A inverse, B, and B inverse. The only rule is that an A can't sit next to an A inverse, and a B can't sit next to a B inverse, because those would cancel. So ab is a valid word, ab inverse is valid, but abed inverse collapses immediately to just A. Every valid word is called reduced, and the set of all reduced words is called the free group on 2 generators. Think of it as a giant tree. At the root sits the empty word. From the root, 4 branches shoot out: A inverse, B inverse. From each of those, 3 more branches, never looping back on themselves. The tree never closes up. Every word is a unique path. The observation that does all the work is this. Take this tree and separate it by which letter each word starts with. You get 4 groups: words starting with A, words starting with A inverse, words starting with B, words starting with B inverse, plus the empty word sitting on its own. Pick the pile of words that start with A. Stick an A inverse in front of every one of them. The A cancels, and what you're left with is every reduced word that doesn't start with A inverse, which, if you think about it, is almost the whole group. It's 3 of the 4 piles, plus the empty word, all at once. So just by prepending a single letter, you've taken 1 pile and transformed it into 3 piles worth of stuff. The free group can eat itself. Chop it into a handful of pieces, shift them around by multiplication, and you've reconstructed the whole group twice over, which is a nice combinatorial curiosity, but a group of abstract words isn't an orange. The bridge, and this is what Felix Hausdorff spotted in 1914, is that the rotations of three-dimensional space contain a copy of this free group. The group of all rotations of space is called SO3. Pick two axes in sufficiently generic position, say two perpendicular axes, and rotate by a carefully chosen irrational angle around each of them. The standard choice is the angle whose cosine is 1/3 around the z-axis and around the x-axis. Call these two rotations A and B. The claim is that if you compose them in any non-trivial way, rotate by A, then by B, then by A again, then by B inverse, and so on, you will never ever get back to where you started. The only way to return to the identity is if your word cancels down to nothing before you even start rotating. So those two rotations generate a perfect copy of the free group living inside the rotations of physical space. Every reduced word in A and B is a distinct, different rotation. The proof that they really do generate a free group is something called the ping-pong lemma, and the geometry behind it is direct. With arcos of 1/3 as the rotation angle, you can carve the sphere into two disjoint regions, call them x and y. Region x is the set of points where applying a non-trivial power of the rotation around z always lands you no matter what you started with. Region y plays the same role for the rotation around x. The two regions don't overlap. The sphere breaks up into a huge number of these orbits, each one completely separate from all the others. So pick one point from every orbit, and call that collection of chosen points M. Every point on the sphere belongs to exactly one orbit, and that orbit has exactly one representative in M. I said pick one point from every orbit very casually. There are uncountably many orbits. There is no formula for which point to pick. You just pick. This is the step that requires the axiom of choice, and we'll come back to the trouble it causes. With M in hand, every point on the sphere can be described uniquely as take a point from M, then apply some specific reduced word in A and B. So the entire sphere is carved up, one point per orbit per word, matching the free group exactly. Now we can run Hausdorff's trick back in the physical world. Sort the points of the sphere by which letter their word starts with. You get 5 piles. Points whose word starts with A inverse, with B inverse, and the points of M themselves whose word is empty. Take the pile whose words start with A, and rotate the entire pile by A inverse. Every word loses its leading A, and the pile you end up with covers 3 of the other piles at once. Do the same thing to the pile starting with B, and it covers a huge chunk of the rest. What Hausdorff actually proved in 1914 is one step shy of Banach and Tarski, one that shows exactly where the free group algebra cashes out in the physical world. He showed that the sphere splits into 4 pieces, call them A, B, C, and Q, where Q is a countable scrap, the troublesome points on the rotation axis, and the remaining 3 pieces have a peculiar property. A is congruent to B by a rotation, A is congruent to C by a rotation, and A is also congruent to B union C by a rotation. So A is the same size as B, and the same size as C, and the same size as B and C put together. That is the contradiction, sitting on the surface of the sphere, written down in 1914. Banach and Tarski's contribution a decade later was to absorb the countable junk Q without losing anything, and to promote the whole construction from the 2-dimensional surface to the solid 3-dimensional ball, which raises a strange problem. Why should that even be allowed to work? Because in the world of the free group, it was just symbol manipulation. But now you're claiming you can cover the sphere twice by physically rotating a handful of its pieces. There's no smuggled volume, there's no duplicated material. Every point gets used, every point ends up somewhere. And yet the sphere, a specific 2-dimensional surface, is now 2 spheres worth of stuff. The answer is that these pieces are not sets you could ever draw. They are scatterings of points, picked out using the axiom of choice, with no shape, no boundary, no thickness. They are not solid regions, they are dusts. Let me be honest here, there are a couple of technical warts. A few points on the sphere, the ones that sit exactly on the rotation axis, get fixed by some of the rotations, which breaks the clean correspondence with the free group. You have to remove a countable set of bad points first, and deal with them separately. There's a neat trick using a third rotation to fold that countable set back into the sphere without contradiction, but the main idea is what I just said. If you're a mathematician, you'll want to read a real proof. If you're not, trust me, the gap closes. Okay, that gets you 2 spheres from 1. But an orange isn't a sphere, it's a solid ball, all the way through. To promote the result from the sphere's surface to the whole ball, think about every point inside the ball except the center. Each such point sits on a unique radius, a line from the center out to some point on the surface. So the inside of the ball, minus the center, is infinitely many scaled down copies of the sphere, stacked from radius 0 out to radius 1. Whatever decomposition works on the surface, works on each of those shells simultaneously, and hence on the whole punctured ball. That leaves one lonely point, the center. This is classic mathematician's mischief. You handle it with another Hilbert's Hotel move. Pick a circle through the center that lies inside the ball. Rotate it by an irrational angle. The orbit of the center under that rotation is a countable set of points inside the ball, none of which ever comes back to the center. Slide everyone up by 1 position along this orbit, and the center spot opens up, filled by its neighbor, whose spot is filled by its neighbor, and so on forever. 1 guest shifts, every room stays full. Put it all together, 5 pieces, 2 identical balls. And 5, by the way, is not arbitrary. Raphael Robinson proved in 1947 that 5 is optimal. You genuinely cannot do it with 4. 4 pieces are enough to duplicate the sphere itself, but the solid ball needs that 5th piece to handle the lone fixed point at the center. The argument turns on a parity obstruction inside the free group decomposition. Any attempt to absorb the center using only 4 pieces forces a word in A and B to simultaneously be its own inverse, which in a free group it cannot be. So when you hear 5 pieces, that number is sharp. 4 would be a different theorem and a false one. So what on earth are these pieces? Imagine trying to assign a volume to the pile of points whose words start with A. You can't use any standard notion of volume, because if you could, then applying a single rotation to that pile shouldn't change its volume. But we just saw that rotating it by A inverse produces something the size of 3 of the original piles. If volume is preserved under rotation, and if the 5 piles together make 1 ball, and if rearranging them makes 2 balls, then somewhere volume was not preserved. Somewhere, one of those pieces cannot have had a volume to begin with. These are the non-measurable sets, objects so pathologically constructed that the question, what is their volume, has no consistent answer. Any number you pick, 0, a half, infinity, leads to a contradiction with the rules that volume is supposed to obey. And if you've never met a non-measurable set before, your reaction is probably that this is a cheat. You can't just wave the axiom of choice and conjure sets that refuse to behave, except you can, and this is what the axiom of choice does. It insists that even when there's no recipe for choosing, a choice exists. It guarantees the output of infinitely many arbitrary decisions made all at once. Most of mathematics leans on this axiom without blinking. Every vector space has a basis that uses choice. Every field has an algebraic closure, choice. Tychonoff's theorem that products of compact spaces are compact, choice. Reject the axiom of choice, and large chunks of modern mathematics stop working in their usual form. You can reject it if you want, some mathematicians do. The cleanest formal statement of what that buys you is due to Robert Solovay in 1970. Assuming it is consistent for ZFC plus an inaccessible cardinal to exist, Solovay constructed a model of ZF, set theory without choice, in which every subset of n-dimensional space is Lebesgue measurable. Every set has a volume. Non-measurable sets simply don't exist, and Banach-Tarski has nothing to work with. An orange stays an orange. The price is the inaccessible cardinal. You have to assume the consistency of a very large infinity that ordinary set theory can neither build nor refute. So rejecting choice isn't free. It costs a specific large cardinal axiom, and Shayla later proved, in 1984, that you cannot avoid that cost. The inaccessible cardinal is doing real work. If you replace choice with an incompatible alternative, say the axiom of determinacy, you get a similarly tame universe, where every subset of three-dimensional space has a well-defined volume, and Banach-Tarski fails outright. The cost is that some familiar infinite constructions become more delicate. You trade one kind of strangeness for another. There is no universe of mathematics where nothing is weird. You only get to choose which flavor of weirdness you're willing to live with, which is to me the actual lesson of this whole story. People often describe Banach Tarski as proof that mathematics has broken from reality, or that the axiom of choice is suspect, or that something has gone wrong. I don't think that's right. The theorem is an honest report about what happens when you take the idea of a point, a dimensionless, infinitely precise location, completely seriously. Real oranges aren't made of points. They're made of atoms, finitely many of them, each with some size. You can't partition an atom the way you partition a set. Banach Tarski says nothing about physical duplication, because no physical object has the uncountable intricacy the theorem needs. It is a statement about the idealization, not the fruit. Pick up the orange again. It still weighs what it weighed. The pieces Banach and Tarski are talking about don't live in it any more than the square root of 2 lives in a ruler. But if you take the idealized ball, the one with every real numbered point of space packed inside it, no gaps, no atoms, just geometry, then that idealization, the one we casually assume behaves like the fruit on the table, turns out to be strange enough to be cut apart and rebuilt into 2 of itself. The orange in your hand is safe. It's the orange in your head that was always stranger than you thought.